Welcome back to your favorite intermediate algebra course here. Today we're going to look at analyzing graphs of polynomial functions. And there's four there's four big statements that we've looked at these last couple sections. That if f of x, if you have a polynomial function and k is a real number, such that f of k equals 0, then you know, first of all, k is a 0. And if you know k is a 0, underline this here, k is a 0, x minus that k is a factor. K would also be one of the solutions when f of x is equal to 0. And also, k is an x-intercept of the graph of f. Okay, so those are four equivalent statements um, for a polynomial function. Now let's do an example here. Let's say you got let's say we're going to graph Alright, let's say we're going to graph that right there. Okay, the first thing I'm going to look at is I'm going to look for my zeros. Okay, now the nice thing about this is it's already in factored form. You got x plus 1 quantity squared, in fact, so you got two of those. And you got this x minus 3, right? So we ignore that constant in front, and then we just solve, for each of these x-intercepts here. So you got x equals -1, you got another x equals -1, you got an x equals 3, okay? So what you have here is you say x equals -1 with multiplicity 2. Alright, so you got two of those is what that's saying. You got two of those x equals -1 as my zeros or my x-intercepts. And then you got this x equals 3. So you already know on your graph, at -1, it's going to cross there. It's going to hit right there, 1, 2, 3, and then you're also going to hit right there at 3. Okay? Now, if you have an even multiplicity, so you hit there at -1 and you have even multiplicity, what that means is you're just going to touch it. So you're either going to just touch like that, or maybe you're just going to touch it like that. Okay, one of those two scenarios there. Now let's talk quickly about end behavior of this thing. Okay, we just found our x-intercepts here, our x-intercepts up here, right? That's what we're looking for, number one. Number two, let's look at our end behavior. Okay, if you were to write this out, in other words, expand this, x plus 1 quantity squared, x plus 1, x plus 1, x minus 3, so you'd have, there's your x squared plus 2x plus 1. You get this x minus 3, right? Take the x through to each of those, take the minus 3 to each of those, and then you have this -1/2 in front. Anyways, you got x cubed plus blah blah blah, who cares? But you take this -1/2 through, finally, -1/2 x cubed plus blah blah blah, right? So this is your function. For end behavior, we're only looking at the degree first. If you remember, you look at that degree, it's odd. It's odd, so it either behaves like -x cubed, which goes down to the left, up to the right, or it behaves, or I'm sorry, positive x cubed, which should go down to the left, up to the right, or it will behave kind of like -x cubed, we go up to the left, down to the right, okay? So you say n is odd, n is 3, it's odd, okay? And finally, the leading coefficient here is negative. It's less than 0, oops, negative. It's -1/2, right? So you know it's got to go up to the left, down to the right, eventually. Okay, so I kind of make a little mark on my big graph here. Up to the left, down to the right. Okay, so right away I'm thinking, oh, this thing's probably going to hit, it's going to kind of loop right there. You know it's got to be that upper loop, if you will. Okay, when it hits that -1. Because then it's probably going to do something like this. And it's going to go up, and they'll probably loop down, because this is a cubic, and it's going to go down like that, okay? But we don't know exactly what this thing does, so we're just going to put a bunch of points on there until we can see it enough to graph this thing, okay? So, oops, let me draw that there. So let's plot points. Number 3, let's plot. points. Okay. Now we already have -1, which the y value is 0, and we already have 3, which is 0. So let's go a little bit to the left here, -1, maybe I don't know, -2. Maybe go -3 if you want to, but let's go to the right of -1, like 0, maybe 1, maybe 2, and then excuse me, and then 4 afterwards. But enough there that we can kind of get a feel for this thing. Okay, exactly what this does. And then we just start plugging and chugging. So let's plug in that -2. So here's our function, -1/2 x plus 1 quantity squared times x minus 3. Okay, and we're plugging in -2. So what is f of -2? -1/2, we got -1 squared. That's -5. Well, -1 squared is +1, so we got -1/2 times +1 times -5, which is 5/2, right? So when I plug in -2, I get 5/2. So -2, and I'm up 2.5, 5/2, right? I could plug in -3 if you wanted to, and it'd spit out, let's see, -3 plus 1, -2, equals 4. 6 is, let's see, that's a -12 there. -12 times -1. I got that 24. So you end up getting 12, +12 there. 312. Okay. So this kind of shoots up. I'm not going to put up 12 clear up there, but you know it already shoots up there to the left, and you hit that 12. Okay. Let's plug in the 0 now instead. 0 plus 1. Alright, so you got a 1 squared there, you got -3, so you got -3 times -1, 3 over 2, 3/2, or 1.5. So 0 comma 1.5. Let's plug in 1. That'd give you 1 plus 1 quantity square 4. 4 times that to the right of it, 1 minus 3, -2. So 4 times that, -2, -8. -8 times the -1, 8. 8 over 2, 4. So you got the 1 comma 4. Okay. Plug in the 2, and you're going to end up with, looks like that's going to be 4.5. Okay. Plug in 4, you're going to end up with -12.5, -12.5. Okay, I kind of cheated on those and just, you look at the calculator if you wanted to on that one, but I'll show you the calculator in a minute. So we got, let's plot those. 1, 2, 4.5. Right there. We got the 3, 0 already right there. We got the 4, and the 4 is like way down there, right? -12.5. So we're like, oh yeah, okay, this looks like it's going to be something like this, right? And then it really shoots down, and we already know that end behavior, that it is going to shoot down, okay? So why don't we look at that, let me punch that in, let me go over to my desk here. Let's punch that in our calculator. Okay, let me turn this on, and we're punching in -1/2 times x plus 1 quantity squared times x minus 3. Okay, it looks just like that. So I go, and if you remember from the home screen to get here, we went lime F1, right, on this TI-89, and it shows you that right there. Okay, and then from here we go zoom, F2, zoom, zoom standard. Gives us a little graph here, okay? All right, now you notice how many curves you got here. You see how you have the one turn there, and you got another turn up here? Okay, these are called local mins and local maxes, okay? But that's how many, those are called turning points, okay? Since this is a third degree um, polynomial, you're going to have at most, if it's nth degree, you're going to have at most n minus 1 turning points. So since it's a third degree, 3 minus 1, 2, you're going to have at most 2 turning points on this thing. Okay, that's at most n minus 1 turning points. If it's a 4th degree, you would have at most 3 turning points. If it's a 5th degree, you'd have at most 4 turning points. Okay, and we talked about last time the amount of zeros. The fundamental theorem of algebra, at least extended into the linear factorization theorem, says if you have a 3rd degree polynomial, you could have up to 3, right, zeros. Now, do you remember this was with multiplicity too? So we had 1, 2, and 3. So we actually have 3 real zeros on this one, don't we? It's just we count that one twice. Okay, that was that negative 1 we hit twice, and then over here it was 3, right? Now here's how you find your maxes and mins with this thing. Okay, you have, and this is called a local minimum, I'm sorry. Do you see how right here, you're, it's the lowest point in that area? And because I know over here, I'm actually go lower, don't I? When I'm talking about my y's, I'm going lower over here. But in this area, it's the lowest point. So the bottom of this little u right here, we call that a local minimum. Local meaning in that area. Okay, if I was to restrict it within these x values right here, that's a local minimum. Okay, and your calculator can find those for you. If you go math, minimum right there, it's your minimum. You have to give it a lower bound, so I've got to restrict the area. So I go to the left of that little u, I go to the right of it, hit enter as well. And you see how it says minimum? Hey, my minimum is right there at -1, 0. It was right on the money for this x-intercept. You see that? Okay. Now up here I got a local maximum. This may not be the max high point of the entire graph, right? That's called a absolute maximum. It's only a local maximum. In other words, within a little area, that's my highest point, right? Because we know we have higher points on this thing. So this is called a local maximum. I do the same thing, F5. I go to maximum, and I say, okay, the maximum is about right there. So I got to go to the left of it. I got to restrict it by going to the left and hitting enter. I got to go to the right of it and hit enter. And you notice that it gives me that maximum, 1.6 repeated and 4.741 approximately. Move that 4.741. Okay, and that's my maximum, and I would say maximum dot dot, and I would write those two coordinates, 1.6 repeated, comma 4.74. Okay, so that's how you find with your graphing calculator a maximum or a minimum. Okay. All right, let's do another one. Let's say you have, let's do negative. You know, let me do it on the next video, actually. Sorry about that.